And now we're on 9.3, stoichiometry of gaseous substances, mixtures, and reactions. In this section, we're going to use the ideal gas law to compute gas densities and molar masses, perform stoichiometric calculations involving gaseous substances, and state Dalton's law of partial pressures and use it in calculations involving gaseous mixtures. Okay, so first we're going to talk about how we can relate density to the ideal gas law. And a few things we need to recall. First is that density is equal to mass divided by volume, or D equals m over V. And we can solve for mass here. And mass is equal to density times volume. One other thing we know is from Pivnert, PV equals nRT. N is moles, and we know moles and mass are related by molar mass. So using a capital M for molar mass, we know that molar mass is equal to our mass of something divided by the number of moles. And so we can solve for our number of moles here, N is then equal to our mass divided by our molar mass. And we can take that and substitute it into Pivnert, and that gives us PV equals m over big M times RT. And now we just solved for mass also from our density equation, so we can go ahead and substitute that in for mass. So we get that PV equals density times volume divided by molar mass times RT. We see we have a volume on both sides, those cancel out. And now going ahead and solving for density, we're going to multiply both sides times m, so that means pressure times our molar mass, and divided by RT. So these are the same thing here and here. So now we get that density is equal, the density of our gas is equal to its pressure times the molar mass divided by the universal gas constant times its temperature. Now, density, remember, is an intensive property. It doesn't depend on how much of the substance there is. But the density of a gas depends on its pressure, temperature, and molar mass. So in this case, before when we were talking about the ideal gas law, we didn't care with the identity of the gas. But when we're talking about the density of it, what it is does matter. So as an example, we want to look at the density of molecular nitrogen at STP. So let's remember what our STP conditions are. Temperature is 0 degrees Celsius, aka 273 Kelvin. Pressure is equal to 1 atm. And then we have nitrogen gas, which means it's N2, so it has a molecular mass of 28.01 grams per mole. And we can just plug all this right into this density equation that we just derived. And we see ATMs cancel from the R, moles cancel, kelvins cancel, and we are left with grams over liters. And that is a density, that is a mass per volume. And gases generally are given density as grams per liter because of how light they are. So we're used to densities of liquids and solids being grams per cubic centimeter or grams per milliliter, but gases are just so much lighter that it's a lot easier to do them in terms of grams per liter. So I kind of already showed this, but we can also relate all of this to molar mass. We looked at this already. PV equals mass divided by molar mass times RT. And we can use that for this next example. Cyclopropane, once used with oxygen as an anesthetic, is composed of 85.7% carbon and 14.3% hydrogen by mass. Find the empirical formula. And then if 1.56 grams of it occupies a volume of 1 liter at 0.984 atms and 50 degrees Celsius, what is its molecular formula? So this is a really cool question in my opinion. It's not something that I've seen really very often until I got this book. And I actually really do like this problem. So the first part goes back to our first exam in those first few chapters, empirical formula. So you take your percentage, turn it into grams. Take those grams, use their molar masses, turn them into moles. Divide by the smaller number of moles, in this case 7.136. And you get 1 to 1.98, that is 2 for hydrogen, so you get an empirical formula of CH2. And the mass of the empirical formula then is 14.03 grams per unit, or grams per mole, however you want to say it. So there's our empirical formula. We've done that first. Now the next thing is we want to figure out the molecular formula. So we need to figure out what its actual molar mass is based off of this information given to us. And we can do that because we have a formula for it. We've derived that equation. We have the mass of it. We know R. We were told the temperature. We had to put it in Kelvin. We know our pressure. We know our volume. And so we put all that in, and we can see liters cancel, ATM cancel, Kelvin cancel, and we get grams times inverse moles, or grams per mole. And we get 42.0. So we take that molar mass, divide it by the empirical mass, factor of 3. So we multiply all of our subscripts by 3, and we get the molecular formula of C3H6. So this is just a really great problem that brings together some of our old material with our new material. And for those of you listening, that's a big hint to your next midterm. I will probably have a question very similar to this on it. So the next question, we are looking at the molar mass of a volatile liquid. And this is actually a really cool thing to talk about how it's done. You take a sample in its liquid form with a little tiny hole in the flask at the top. So the liquid becomes a gas that escapes through the hole. Take the flask away from heat right when all the liquid becomes gas. And now the flask is only filled with gaseous sample at just regular room ambient pressure. You seal the flask, let it become a liquid, and then you weigh it to figure out the difference in the mass from when that was all liquid and then some of it evaporated off, and now you look at what's left over. So doing this, we had some chloroform gas weighing 0.494 collected in the flask with a volume of 129 cubic centimeters at 99.6 degrees Celsius, when the atmospheric pressure 742.1 millimeters of mercury. What is the approximate molar mass of the chloroform? So we know that M for molar mass is M over N. We know that N equals PV over RT. Substituting that in, we get that our molar mass is equal to our mass times RT divided by PV. Put in all of these numbers. Liters here cancel, ATMs cancel, kelvins cancel. We get grams per mole. We get 120 grams per mole. And this is an example of this procedure. So we have one more gas law to talk about from our ideal gases, and it is called Dalton's law. And Dalton's law is probably the most challenging of all the laws. Ready for it? The total pressure of a mixture of gases is equal to the sum of the partial pressures of the components. So P total equals PA plus PB plus PC, etc. Super hard, I know, right? So it's literally, this is the law of partial pressures. And partial pressure just means, okay, this is the pressure of gas A. This is the pressure that the gas would exert if it was by itself. It's my favorite gas law. So if I have these 3 gas cylinders with these 3 pressures, you put them together, the total pressure is equal to just literally adding up their individual pressures. We can express this in terms of mole fractions. So the pressure of A is equal to number of moles of it's a mole fraction, XA, and that is the number of moles of A divided by the total number of moles in the system times the total pressure. And then you can do the same for B and C. Let's look at an example. A 10-liter vessel contains that much hydrogen, helium, and neon at 35 degrees Celsius. What are their partial pressures and the total pressure in atmospheres? So literally, they're all independent of each other. So each one, we're just going to use PIV-NERT for. PV equals nRT. P equals nRT over V. Okay, we're told our N's. We know our temperature. We need to add 273 to, so we have 308 Kelvin. We're told the volume of the vessel is 10 liters. Plug and chug, and you get atmospheres for your pressures. So now you have each of their partial pressures. The total pressure, you add them up, and you get 9.61 times 10 to the negative third ATM. Let's look at a little bit more challenging one. Gas mixture used for anesthesia contains 2.83 moles of oxygen and 8.41 moles of nitrous oxide. The total pressure is 192 kilopascals. What are the mole fractions of oxygen and nitrous oxide, and what are their partial pressures? So the mole fraction, remember, is given by the number of moles of each one divided by the total moles. And the partial pressure is equal to the mole fraction times the total pressure. So for oxygen, it has 2.83 moles divided by the total moles, which is 2.83 plus 8.41. So its mole fraction is 0.252. These are unitless. So then its partial pressure then is 0.252 times 192 kilopascals, the total pressure, and so it's 48.4 kilopascals. Same type of thing for nitrogen. You get mole fraction of 0.748 and partial pressure of 143.6. The other thing that you may notice here, looking at these mole fractions, since there's only two gases in the system, you could have also done 1 minus 0.252. That's saying basically 100 minus 25%. So all the fractions, all the mole fractions need to add up to be 1, because that's totaling the whole. All right, so let's talk about another way you can use Dalton's law of partial pressures. One way that gases are collected and then quantified is by collecting them in an inverted bottle that's been filled with water. So you have a bottle or a test tube, and it's all the way filled with water, and then it's submerged also in like a beaker of water. And you have whatever your reaction is, some gas that's being made, and you put it in a little tube that bubbles it into the test tube. And what happens then is this gas displaces the water. And then you can look at the amount of water displaced, the volume of it, and you can relate that to the amount of gas made. But what's happening though is as the gas is going through the water, it's grabbing water vapor. And so the total pressure of the gas mixture is equal to the atmospheric pressure. So this is again what it looks like, a lot better than I drew it. So your total pressure of the system is equal to the partial pressure of water vapor plus your pressure of whatever your gas is. So for instance, if it's hydrogen gas. So where PT is atmospheric pressure, and then you have your partial pressures of the water vapor and the hydrogen. Now this vapor pressure of the water, it depends on the temperature of the water. And this is the pressure exerted by water vapor in equilibrium with liquid water in a closed container. This is an intensive property. It has nothing to do with the amount of water, but it is very much so temperature dependent. The nice thing though is it's been found for you. So if you're doing this type of problem, it'll tell you the temperature of the water. So you then need to look up what the vapor pressure is. There's some that are on graphs. So here's an example of a graph here. This is from your book, figure 9.22. There's also, along with this figure, a table in your book, table 9.2, that gives you temperatures of water in degrees Celsius and then the vapor pressure in torr. So you go, oh, okay, so my water was at a temperature of 30 degrees Celsius. I look at the table, it has a pressure of 31.8 torr. So then you know that, you generally know your atmospheric pressure, you can then calculate the pressure of your gas. For example, 2 liters of argon collected over water at a temperature of 26 degrees Celsius, pressure of 750 torr in a system. What is the partial pressure of the argon? So we know our total pressure, 750 torr. And we can go ahead and look up the partial pressure of water, and then we can calculate the pressure of the argon. The argon is going to be equal to the total pressure minus the partial pressure of the water. You look it up. Appendix E in your book also has a table. And so it's that 750 torr minus the vapor pressure is 25.2 torr, and you get it 725 torr. Notice it's not that much of the pressure that you have from water vapor, but it's enough that will skew your results if you don't account for it. Your book just kind of touches on this. It's something to be aware of, that it might pop up. Gases are reactants in products, chemical reactions. So you can use the ideal gas law and a balanced chemical equation to relate pressure, volume, temperature, and moles and grams of a gas in a reaction. Remember, we have mole fractions, we have balanced reactions. If you know the grams of something that you used or that you made, then you can get the moles of it, and then you can use the ideal gas law. So don't forget, these all relate to each other. You can also use these stoichiometric factors to relate the moles of the substances. So, we've used that before, and then again, you can use the gas law. And then you can use Avogadro's law as well to use the volume ratio of any two gases in a reaction at a constant temperature and pressure. It's the same as the mole ratio in a balanced chemical reaction. So think Avogadro's law. Volume is proportional to moles. V equals some constant times N. The volume of a gas is directly proportional to the moles of a gas. So for example, nitrogen and hydrogen combine to form ammonia. 1 volume of nitrogen is going to combine with 3 volumes of hydrogen to form 2 volumes of ammonia. A little example here. Propane, we're using it reacting with oxygen at 25 degrees Celsius and 760 torr. React with 2.7 liters of propane measured under the same conditions. And we want to figure out our volume of oxygen here. So we can look at this and say, okay, 1 volume or 1 mole, remember they're proportional, plus 5 volumes of oxygen is going to give us 3 volumes of carbon dioxide plus 4 volumes of water. And so then we know then, we're told 2.7 liters of propane. So I have 2.7 liters here, and then I know from this equation here that I need 5 volumes of oxygen for every liter of propane. So 5 liters of oxygen per 1 liter of propane, and I get 13.5 liters of oxygen. Now, you could do it that way. You can also still use PV equals nRT, but this method works very well and very quick. Here's another example, given some data for nitrogen, hydrogen reacting to form ammonia. We want the volume of hydrogen to make 683 billion cubic feet of ammonia. So looking at our ratios, we see that there's 2 ammonia for 3 hydrogen, or 3 hydrogen per ammonia volume. So that means 3 billion cubic feet of hydrogen per 2 billion cubic feet of ammonia. So 683 times 3 over 2, 1.02 times 10 to the 3rd billion cubic feet. Okay, here's another example. Volume of hydrogen to make 8.88 grams of gallium with an excess of hydrochloric acid. So we're already told that gallium is our limiter here. So first things first, though, we're given grams of gallium. We always need to make sure that's moles. And we can go ahead and go from grams of gallium to moles of hydrogen using our stoichiometry. So first things first, gallium to moles. So we'll write this how we've always kind of done it, 8.88 grams of gallium to moles. So we use molar mass, 1 mole of it for 69.723 grams of gallium. Grams cancel. Now we can go to moles, and we see we need 3 moles of hydrogen. We make 3 moles of hydrogen per 2 moles of gallium. And then we stop there because we don't want grams of hydrogen. We actually want moles because this is the ideal gas law. So we plug that into our calculators and we get 0.191 moles of hydrogen. Now I have my moles of hydrogen. I know my temperature, just got to make it Kelvin. I know my pressure, got to make it ATMs. I've got, and I want my volume. So PV equals nRT. Our volume is equal to nRT over P. I know my N, I know R, I know T, I know P. We can solve this. So our torr is equal to 0.951 ATMs, and we changed our Celsius to Kelvin. So we see Kelvin cancels, ATM cancels, moles cancel. We're left with liters. We get 4.94 liters. So this is also a really good example of something that might pop up on an exam, using a balanced chemical equation and having to relate it to ideal gas law. Just another example, greenhouse gases. This is how what's happening with climate change is that sun is putting in this radiation, and normally a lot of it we're able to bounce away from the atmosphere, but we've got this the greenhouse effect, and what's happening is these greenhouse gases trap that infrared radiation here and then bounce it back to the Earth. So instead of it going away from the Earth, it's coming back and heating up our surroundings. And this is evidenced by the tracking of this carbon dioxide volumes over the year. A lot of people that argue against this try to use kind of this graph here and say, oh, look, there's these constant trends. But when you look at where modern civilization is, it's not going down. It's continuously going up, and it's going up at an alarmingly fast rate, where we've surpassed the 400 ppm concentration. Susan Solomon is a very well-known and respected climatologist. I've actually known a few people who have worked under cool person, really cool work. And I believe that does it for this week's lectures. I will see you all next week with the next half of Chapter 9.